Let's solve for equilibrium concentrations. And for this example, let's have it be for the ionization of a weak acid. So let's imagine the problem statement is, what is the pH of 0.5 molar acetic acid? So we're given that we've got some acetic acid, so I've drawn the structure of acetic acid here. And you might remember that acetic acid is a weak acid. So all the acids that have this carboxylic acid structure, they're all weak acids. So that means that for the most part, when they dissolve in water, they just stay in the structure, and only a small fraction of the molecules end up losing a hydrogen ion to become the corresponding anion. So in this case, the acetate anion. Okay, so this is a weak acid, so we want to know how much of it is going to form H+, because once we have H+, we can calculate the pH. And we'll write down the formula here that pH is the negative log of the hydrogen ion concentration. And note that this is not a natural log like we've been using for other stuff. This is a base 10 logarithm, so that's what we use for pH. Okay, great. So we have all the things we need to calculate the concentration of hydrogen ion. Oh, one more thing we should note before we go on is this abbreviated format here. So when we're working acid-base problems, it's a pain to write out the names of some of the acids. They're a little bit long, and the structures, of course, that takes a lot of time. So we just abbreviate sometimes. So since acetic acid has one acidic hydrogen, we can just abbreviate that as an acid with one acidic hydrogen. So just HA, so it just means some weak acid. And since it can lose its H+, what leaves behind is the anion A-. So in this case, A- is acetate and HA is acetic acid. But this sort of focuses our attention on not what the specific acid is, but just the numbers and what the equilibrium constant is. This equilibrium constant, by the way, because it is for an acid dissociating like this, is given a special name. We call it a Ka. So a Ka is just a subclass of equilibrium constants for the acid ionization reaction. All right, let's work the problem. Okay, so we have our weak acid, and we've got a Ka of 1.75, 10⁻⁵, and we've got a concentration of acid of 0.5 molar. So we took, for instance, half a mole of acetic acid and dissolved it in enough water to make 1 liter. We want to know at equilibrium what are the concentrations of all these things. We call this C0 because this is saying before it reacts what's the concentration of this, because after we're done it will be a little bit lower because we're going to form some of these. So this will be a tiny bit lower than 0.5. Okay, so to do this we're going to do an ice table, initial concentration, change in concentration, equilibrium concentrations. Let's use units of molarity. It's customary for doing aqueous equilibrium problems to use a 1 molar standard state. So unless there's a good reason for thinking otherwise, use molarity. All right, so we have initial, change, and equilibrium. And let's put in what those were. So initially we had 0.5 molar acetic acid before it reacted. And we dissolved this in pure water, so we don't have very much of this. So we'll say that we don't have any acetate ion yet and no hydrogen ion. What about the changes? Well, for every mole that reacts, we're going to lose a mole here, gain a mole here, and gain a mole here. So we check our coefficients and they're all 1, so it's very simple. All right, so at equilibrium, we're going to have 5 minus x. Here we're just going to have x, and here we're going to have x. And let me write our expression for K equilibrium. K equilibrium is equal concentration of reactants over products. So we've got concentration of our acetate, concentration of hydrogen ion, divided by the concentration of intact acid. Great. Let's put in our numbers from our ice table. So we've got x times x all over 0.5 minus x. Okay, now when we do this, we think, oh, this is too bad. We've got a quadratic equation. This is going to be rather a nuisance to solve. Well, whenever we have things added or subtracted like this, we can make an approximation that will save us from having to do the quadratic formula. And if, depending on the stoichiometry, we can end up with a cubic equation, and then we really want to use approximation methods because they'll make it easy for us to do. Okay, so we've got this expression, x squared over 0.5 minus x. So we ask ourselves, what if x is much, much less than 0.5? If x is much, much less than 0.5, then the bottom is going to be just approximately 0.5. And this will be really easy to solve. In fact, it will be trivial. So let's do that on the next slide. So what we're going to do is assume that x is much, much smaller than 0.5. And then at the end of the problem, we'll check and see if that was justified. Now remember, x is how far we're reacting in the forward direction, and the k for this was an order of magnitude 10 negative 5. So we expect that we're not going to be able to go very far. So x probably should be a small number. Let's see if that's true. So if this is true, then we can say k equilibrium is approximately equal to x squared over 0.5, because x is small enough to ignore. Well, in that case, it's going to be really easy to solve for x. We multiply both sides by 0.5 and take the square root. Okay, so we have this, and because we aren't sure if we're going to keep this is called x1. It's our first approximation of x. x1 is going to be the square root. And this comes out to 2.96 times 10 to the negative 3. So I have to ask, were we justified in saying that this number is a lot less than 0.5? Well, it is. That's 0.003 essentially, much less than 0.5. So if we were still worried about it, what we could do is do a second iteration. We can say, okay, I've got that k equilibrium is equal to x squared over 0.5 minus x. And to avoid using the quadratic formula, I'll just plug in my x1 down here. Since this is a number we've already calculated in the first iteration. And then we can solve for x2. So we just multiply both sides by this, and then take the square root. So we multiplied k equilibrium times 0.5 minus x1. If we write that out in full, we get x2 is the square root of k equilibrium, 1.75, 10 negative 5. And then we have 0.5 minus x1, and x1 was 2.96 times 10 negative 3. All right, and what does that come out to be? x2 is equal to x2 is equal to 2.95 times 10 to the negative 3. Now notice x1 was 2.96 times 10 to the negative 3, so we're converging really rapidly on the answer. So since our original data was only 1 sig fig, we're justified in stopping and saying, well, we're now accurate. We're now converging at the third figure rather than the first significant figure, so this is plenty accurate. Actually, it's kind of overkill. So we're ready to stop. Now what is x2 equal to? Okay, so we get our final answer for x2, and we've decided that that's plenty precise enough. And so now we're going to use it to get our concentration. So we go back to our ice table, and we can see that the concentration of hydrogen ion was equal to x. So we've already calculated the concentration of hydrogen ion. So let's write that down. Concentration of hydrogen ion was equal to 2.96, 2.95, 10 to the negative 3 molar. And the pH is the negative log of the hydrogen ion concentration. It's a negative log of the hydrogen ion concentration. And that comes out to a pH of 2.53. So there's our pH. So in this video you've learned how to apply equilibrium constants to weak acid ionization problems, but also you've learned the method of successive approximation.